So today we have Thomas Dullien. Thomas built a very successful 20-year career in computer security, after which he decided to focus on performance. He co-founded Optimized.cloud because he believes that in the cloud computing, efficiency equals money savings. And because he thinks there is a huge opportunity to reduce superfluous computation and hence energy use. Thomas, welcome. Thanks again for allocating time in your busy schedule. While I was preparing for our conversation, I was set to watch your presentations, but quickly found that that I would need at least 1 week, to catch up. So, yeah, I mean, that's a really impressive list of talks and contributions that you made over the years. So,
thank you.
Just wanted to say that.
Although most of them are not. Yeah.
Sure. Yeah,
well, thanks.
go ahead.
I'm trying to figure out how much latency we have in our conversation because it seems to be quite a bit. Yeah, so a lot of these talks are not so performance-centric though, so no need to catch up on all of them. Sure.
Yeah, but actually, so since you have such an impressive career in security, let me just start with that, and then we'll transition to performance. So you have a huge experience in security. Do you think that security and performance have anything in common?
Yeah. So in fact, they do have some things in common, and sometimes they're allies, and sometimes they're the antagonists. So the first thing about like the biggest commonality between security and performance is that a lot of the offensive security work is about analyzing and understanding very legacy systems, and then identifying places where there are problems in these systems, and then that work usually spans a lot of different abstraction layers. So it's very high-level design criteria down to the very low-level what is happening at a particular address in memory. And what happens in security normally is when you find problems, then people are quite mad at you because they now have to go and fix them. And performance is similar in the sense that if you have an existing large-scale system, you're usually also looking at a very large existing code base, and you need to know where the problems are. The big difference with performance work is that when you do identify problems and you manage to fix them, then people are usually quite happy because now everything is running faster and cheaper. So I think the big similarities are that both require a sort of, like to do it well, they both require a sort of whole stack understanding, meaning being able to go from the high-level design elements down to what is happening with the memory allocator, what is happening with the pointers here, what's the disassembly generated from the compiler.
Right. Do you find similar problems in security and performance, like for example, code similarity analysis?
So I find the tools that we've built for doing patch analysis, so background, about 15, 16, 17 years ago, actually 18 years ago by now, I built a reverse engineering tool that was designed to analyze Microsoft security patches. So when you had two versions of the same binary with just a minor change and a bunch of compiler-induced changes, the tool, which is called bindiff, was useful for analyzing secure patches. And I found that having such tooling is useful for analyzing different versions of the same binary compiled with different compiler settings. Because as awesome as something like Godbolt is, the effects of something like link time optimization, which can affect essentially your entire binary, they're not easily identifiable by just pasting something into the Godbolt webpage. So sometimes it's actually quite useful to be able to binaries and then compare the binaries and see what have these changes in compiler settings done to the overall layout of the binary.
Right. Yeah. So in one of your talks, you were talking about so-called contained complexity. So first of all, so please explain what's that, and then The follow-up question is, are you worried that improvements in hardware, well, and software actually as well, come at the cost of increased complexity, and maybe they impose security challenges on us?
So the talk about complexity and security, meaning containing complexity, what that talk is really all about is that when you look at what's happening in computer security, where we have a lot of insecure devices, let's say a internet-connected coffee maker, that can be hijacked and that can be made to do something very different. People are surprised that I can take a coffee maker and then make the coffee maker do something very different. But the reality is we're putting all sorts of general purpose CPUs in all sorts of devices. We're essentially putting ARM cores into the world like we put salt on food. And the talk is mostly about how we have cheap complexity in that sense. We're, instead of putting a very simple electrical circuit into a coffee maker that just allows it to make coffee, a highly complex full CPU into it, because complexity is actually cheaper than simplicity nowadays, because you can get a core for really cheap and then specialize the core in software to do something simple, and that's cheaper than to just build something simple in the first place. So the entire talk really is about how general purpose computation is seeping into everything. And the place security and performance are antagonistic at times is certain security features will have a performance impact. And then quite often when you propose these security features, people will push back, arguing about the performance impact. And I think, I mean, I've always been interested in performance. But part of the reason I got interested in performance was people pushing back on something that cost a few percentage point of performance in a code base that had many more performance sins lying around. So there was a joke, hey, what if we, like, you're saying no to the security feature because it will cost you 3% of performance, but what if we go in and find you 8% of performance? Will we get 3 of that for security?
All right. Yeah. I actually like how you compare salt and ARM cores. That's beautiful. Yeah.
Yeah, it's quite crazy. I mean, if you look at a modern USB cable, you'll end up with, like, or a modern Lightning connector, you'll end up with what, two ARM cores in the cable. It's quite insane.
Yeah. Okay. So Thomas, so why you decided to switch from security to performance?
Right. So security is a super interesting field, but at the same time, security is also always, to some extent, about human conflict. Like, you're always securing something against somebody else, and you're always working for somebody against somebody else. And over the years, as I got older, I got a bit tired of having to pick a side to work for and a side to work against. And also, as I got older, I got a little bit more environmentalist. And I was wondering, hey, should I perhaps just, join, let's say, Sea Shepherd or another environmental organization and devote my time full time to it? And I wondered, is there a place where I can make use of my experience and my abilities that isn't about human conflict, but that has a potentially positive environmental impact? And then I thought a little bit, and I ended up with performance, which happens to be both technically really interesting and then economically quite interesting because it makes stuff cheaper, and then ecologically interesting because you make stuff cheaper by saving on energy.
Okay. Yeah. That's important for sure. So okay, so let's start talking about performance in the cloud, and let's start with the question: is Moore's law dead?
That's a really, really good question. I think you would probably want to talk to somebody that works at a chip manufacturer. What I would say is that there's many versions of Moore's law, And the version that said the unit costs for transistors are still falling at exponential rate with a doubling of about every 18 months, I would say the economic version of Moore's law is dead. The cost per transistor, the device cost, is not falling at the same rate that it used to fall anymore. I mean, the chip makers are still making progress in shrinking transistors. The capex involved in the research, and then the cost of actually producing those transistors on the same curve anymore. So Moore's law in the economic sense is, if not entirely dead, it's certainly not what it used to be.
Right, but what would you say, like, from the software vendor's perspective, is Moore's law dead?
I mean, from the software vendor's perspective, it's a bit difficult. What is a software vendor these days, right? I mean, if you look at something like Snowflake or somebody like Spotify, are these software vendors in the classical sense? They're providers of digital goods for the most part, right? So the classical software vendor is much less there than they used to be. Even if you look at Adobe, like Adobe moved from selling software, being a classical software vendor, to be essentially a software as a service with the Creative Cloud and so forth. So in some sense, the move to the cloud has shifted the cost of computation from the software vendor now a goods provider or a software as a service. And I think that shift of the cost of computation is quite relevant because for us as performance-oriented people, 15 years ago, very few places really cared about software performance. But now, because in the end the user of the software had to pay for it. But now that the cost has shifted to the vendor of the software, that's a very different setup.
Right. So essentially, what you're saying is that software vendors cannot rely anymore on chip manufacturers, right? And should pay attention to and actually spend the human resources and optimize their code, right? Is that what you're saying?
Yeah, I mean, yes. Yeah, and you see that already in with the hyperscalers, right? If you look at the sort of performance infrastructure that Facebook and Google had to build internally, also the trend to hardware offload. If you look at Google's trajectory, right, they start out building a lot of very, very impressive performance monitoring infrastructure in around 2008, 2009, 2010, and then that created visibility into where cycles are going. And then you look at stuff like the tensor processing units. Those things were built with an economic need. Like once you get visibility into a large fleet where you're spending your cycles, and you realize that a certain new feature will not be realizable with your current hardware, and you'll need to do custom hardware offload,
right.
You're already deeply into the territory of spending human expertise versus just adding more cores. And then you can pretty much see this. The trajectory was tensor processing units, and now Google published a paper a few months ago about having offloaded a lot of video transcoding into custom hardware. And what I can say is that when I was still at Google, I regularly checked the profiling infrastructure that Google had for the most expensive piece of code they're running. And FFmpeg doing video transcoding was very regular at the top of the list. So I'm not surprised that at some point they're like, oh, this is getting so expensive. At this point, it's actually worth spending the money to have somebody design a custom chip and well, hire a fab to actually make it.
Right. Yeah. That's super interesting. I was actually planning to dig into it later, but I mean, since we are here, let's dive into that. Yeah. I mean, so and actually, I think that the cloud is actually a unique, a unique environment where you can easily have a whole variety of different hardware, and you can allow yourself to to offload whatever workload to whatever hardware, right? You can offload it to GPU, FPGA, TPU, like you said, any other accelerator, right? So that's a unique opportunity here. But what do you think about the again, the complexity that comes with that? What I mean by that is that since well, I mean, you will not write the code for GPU or whatever other accelerator as you write code for CPU, right? Because those are massively parallel devices with different architecture. So do you think that this will require a shift in the paradigm and the way we write code nowadays? Because I mean,
yeah, I mean,
you see what I mean, right?
yeah, definitely. I mean, you can already see that paradigm shift, right? If you think about something like Torch or TensorFlow, they are really programming languages masquerading as a Python library. If you think about what they're doing is, they pretend to be a Python library, but really what they're trying is to force regular people into programming in a way that can easily be auto-parallelized onto a GPU. So we're already seeing the paradigm shift in software to some extent. And I think as we're moving more and more into an XPU style architecture, where you have a CPU for general purpose computation and then different accelerators for different things, we'll see more of that. And if you rewind 15 years ago, you would have told people, hey, you need to write stuff in this special programming language so that it can be auto-accelerated. People would have laughed at you to some extent. And nowadays, people pretty routinely write CUDA code. People pretty routinely use vectorization instructions like AVX 512 compiler intrinsics, which in the end is a custom programming language if you want. So I think the time period from, let's say, 1990 to 2010 was probably one of the calmest periods in computing when it comes to programming paradigms. And we all took the 20 years of relative calm for granted. And everybody's now a little bit surprised at how quickly things change. And that's exciting as well, right? Because for 20 years, there was industry-wide consensus on how to build a CPU, what a compiler should do, and so forth. And now as Moore's law is slowing down, things get more heterogeneous and more interesting because the demand for performance is still there, and we now need to figure out ways for how to provide it. So long story short, things are changing. I think we will stick to very similar programming paradigms for a lot of the workloads, and then specialized workloads will be increasingly offloaded to specialized accelerators.
Right. Yeah, that makes sense to me. Now let me also dive a little bit even more deeper about that. But I guess today we're doing a depth first search, if you will. So let me see. So in the cloud, you also have the opportunity to inject the telemetry systems, right? Where you can monitor the workload and dynamically dispatch the workload from one hardware to another hardware. Sorry about that. Do you think that this will be something that we can do, or maybe we already are doing that, like a dynamic dispatching?
Yeah, so I don't see a lot of dynamic migration of workloads to different hardware yet, outside of perhaps autoscaling in some sense. But clearly, the entire cloud model is full of really interesting opportunities. So if you look at something like what Amazon doing with Rubicon, right? And I think, as far as I know Azure is on the path to doing ARM cores as well. There's an argument to be made that if you are a cloud provider and you can actually measure real workloads across your entire cloud, you have an unfair advantage in the CPU design. Brendan Gregg in a recent talk mentioned something similar, where the current CPU manufacturers usually have a much more limited view into what code is actually running everywhere than a cloud provider would have. So there's a strong argument to be made that cloud providers will gather telemetry about the workloads that people actually have, and then use that telemetry to build better chips. And that's an interesting interesting dynamic because for somebody like Intel or AMD, they will probably want to have that sort of data as well, but it's unclear how they're going to get it unless they become cloud providers. So step one, I see the data collection in the cloud that will then feed into chip manufacturing to be really interesting. With regards to dynamic dispatch, this is extremely interesting because you could do things like, let's say you observe that a workload has a lot of L2 cache misses or L1 cache misses, let's say. You could, in theory, try to migrate that to a machine with a bigger L1 cache and then see if that improves performance. And I think there's a whole bunch of other really interesting things that you could do in terms of trying to do per function compiler optimization and so forth in the context of bigger work. But I think it's very early days. Like I don't see the cloud providers having put enough R&D and resources into this just yet. Because cloud is still growing at such an aggressive rate. And with regards to the importance of performance, I think performance is much more important now than it was, let's say, 5 or 10 years ago. But I think we're still at the beginning of that curve. Like I predict that performance optimization and efficiency in the cloud is going to be way more important 5 years down the line and 10 years down the line, to the point where we will eventually have the equivalent of the CIO, like a C-level executive in organizations that's responsible for the efficient delivery of digital goods. That'll take a while to crystallize, but eventually efficiency in delivering your digital goods is going to be a fairly high-level priority in many companies, and that'll then drive product innovations on the side of the cloud providers, if that makes sense.
Yeah, I mean that definitely makes sense to me. I'm giving my +1 to last thought, so definitely, yeah. But let me go back a little bit to the point when you were saying that the cloud service providers are getting telemetry and that it's not available for chip manufacturers. So and I actually immediately see another risk here is that okay, so now, for example, let's say Amazon, for example, will build the best chip that will run in their infrastructure, right? Well, since they can optimize for all the workloads that are running in their cloud, and if they will do that, they might decide to close their ecosystem from the rest of the world and create some kind of monopoly, I would say. So well, I mean, this will be also not I think the best outcome for us, right? And for developers as well.
Yeah, I think you're touching on a very interesting. Oh, sorry. You first. I interrupted you. Sorry.
No. Please go ahead. I was just thinking out loud.
Yeah. So my thought on that is you're touching on a very interesting point, because there's a fundamental disalignment of incentives between a lot of cloud customers and a lot of cloud providers, in the sense that for the cloud customer, the majority of cloud customers want utility computing. Like before cloud was a thing, Sun, while they were dying, pitched this idea of grid computing and utility computing. And utility computing, the entire argument is that computing power should be like water from the tap. You open the tap and then you have as much computing power as you need. And the cloud kind of, but then utilities don't have high margins, because utilities provide a homogeneous good and the competition is fierce and customers can switch easily. And in some sense, customers want utility computing, and cloud providers all want to be the next IBM, meaning they all want to have cust into their infrastructure for the next 50 years, because that's how you get actual margins. And it's a bit unclear how this will play out, right? Because if you look at Google, how they're pushing Kubernetes and GKE and so forth, Google is trying to argue, build all your workloads in a way that's it's portable, so you get closer to utility computing. And there's strong arguments to be made that using the value-added services that Amazon and other cloud providers are providing is actually the right business choice for many companies instead. So all in all, it's quite interesting because I share your concern that the cloud infrastructures can become very, very monopolistic or oligopolistic and very closed and somewhat incompatible with each other. But at the same time, having a closed loop between the workload that's running, the chip design, the accelerator design, and the compiler design is something that's extremely valuable economically if you look at the efficiencies that you could have if you have these things integrated.
Right. Yeah, that's for sure. Yeah, that's true. Okay, now let's now go back and unwind and let's talk about the and let's forget about the offloading and acceleration and all this stuff. So what is the typical workload that runs in the cloud, or there is no such typical workload?
So I think there is no such typical workload. Workloads are super heterogeneous, which is part of the allure and part of the problem. That said, there's classes of workloads, right? There's just a lot of Java backend code that runs in the cloud. There's a lot of people running databases in the cloud. You have a lot of Python code running that's a very thin layer over C++ libraries that they're calling into. Yeah, it's super heterogeneous. And I guess the only commonality between most of the workloads these days is like Linux is ubiquitous. There isn't really a significant other operating system. And the majority of compute is still on x86. What I do find interesting is that the arrival of Linux in open source and the fact that the majority of workloads are majority open source has made stuff like Gravity possible in the first place. Because if you think about it, 15 years ago, the majority of workloads that people were running were closed source, oftentimes on Windows, almost x86. So if somebody had launched, or I mean, you can argue that Sun partially failed because of that. Like, you can't easily push a different CPU architecture in such a scenario. But now, almost every piece of software that anybody's running is one recompile away from just working on a different CPU architecture. So that's a really interesting change that we didn't have before. And yeah, and you can see that the adoption rate for Gravitron is really quite fast. So people are switching CPU architectures. Yeah, which perhaps to summarize, the two characteristics of cloud workloads are A, most of it is open source. So the majority of the money you're spending is actually not spent on your own code, but on third-party libraries that are open source, or on third components that are open source, or on databases that are open source. And the second part is that almost everything is running on Linux in some sense.
Yeah, that's interesting. Now, what is the typical performance bottleneck in the cloud applications?
That's extremely heterogeneous as well. I mean, the classical performance, or the classical scaling bottleneck for everybody is always the RDBMS they put into the middle. Like, people get hit by database issues very easily when they try scaling. That has nothing to do with any low-level optimizations and so forth. So these things are often architectural in nature. But then, when it comes to actual code bottlenecks, it's quite strange how heterogeneous it can be. One of my favorite things that we're seeing over and over. Brief. Can you still hear me? Hello?
Hello. Yeah. We can hear you. Yeah.
Okay. One warning: my telephone may be on the battery in a moment. So if I disappear, I will be back in 5 minutes when I have driven home to the phone charger. So yeah,
Sure.
in terms of heterogeneous, or in terms of things that are often performance bottlenecks in the cloud, one of my favorite one is when people use Amazon in the default, like instances in the default config, the clock source is configured in a way that getting the current timestamp will cause a syscall and a user space kernel space transition. And they're very unexpected for many workloads, because in a normal system you have the VDSO that stops that from happening. So you sometimes see like a Cassandra cluster or a Scala cluster, where if you start measuring where they're going, you end up with like 15-16% are being spent in the kernel getting the time of the day or getting the current timestamp. That's really just a config change then, where you save 10-12% of total cycles immediately. Other funny places where we've seen performance go is Kubernetes does a recursive directory scan of every running container once a minute, because they need to do disk quota accounting, and disk quota accounting under Linux, something that's file system dependent, and Kubernetes doesn't want to be tied to a specific file system, which means in order to do disk quota accounting, they need to do these recursive directory scans. But people don't realize this, and then they ship containers into a big Kubernetes cluster, and that container may contain, let's say, a big file system with a few million files in them. So if you ship containers with a lot of files, what may happen is that instead of your container itself not eating much CPU, Kubernetes will consume quite a bit of CPU just enumerating these files, and you can actually end up exhausting your I/O ops in the cloud from doing stuff like this. Perhaps the rule of thumb is performance or cycles get wasted in places where people don't expect them to get wasted. Oftentimes in third-party components, and oftentimes in environments where nobody looked before, if that makes any sense. There's always an element of surprise where if you talk to a dev and you tell them, hey, we see this piece of code here is eating, let's say, 15% of total CPU time, the developer's like, that cannot be true. This is really weird. And then you dig into it and you find some surprisingly silly reason why you're spending a lot of time there.
Right. Yeah, that's interesting, and we will actually get back to that a little bit later. But I also think that, first of all, we should point out that there are actually two let's say types of workloads that run in the cloud. First, the cloud service providers and the giant companies like Facebook and Google, they have their own services, which also can be considered run in the cloud. But here you were talking about the user applications that run in the cloud ecosystems like an Amazon and Google Cloud and so on and so forth, right? And so yeah, and then I was also interested, in the low level, let's say, categorization of those workloads and their typicals, because, for example, there was a paper from Google, right, where they characterized and actually published the data that which is actually, again, unique in a way, that 30% of the CPU cycles for their Google Cloud services was spent in the CPU front end, like fetching and decoding instructions, which I haven't seen in any other workloads. This can be explained that their binaries are so huge, and the amount of code written is just enormous. So do you have like a similar break for user applications? Maybe do you have maybe some insights of what those numbers can look like?
Yeah, so we don't have good insights in function coding and so forth, like how that breaking amongst the different areas of the CPU is. Mainly because we don't gather data using, or we can't gather data using PMCs, because we strive that our performance profiling tools run on cloud instances which don't have PMCs enabled. So I can't give a good breakdown there, but I can give some data around where people spend most of their CPU time and how they optimize stuff. So one of the somewhat perhaps depressing or funny things that I learned over the last 2 years was that in a lot of places which run garbage collecting languages, let's say particularly Java, and there's more people running Java than I had anticipated coming out of Google, because Google is very C++ heavy, and then some Go, a little bit of Java as well, but the majority of non-Google, non-Facebook infrastructure likely runs on Java. And then the somewhat depressing thing that we learned is that for many Java workloads, the way people optimize CPU performance is actually just reducing the allocation rate for new objects. So because in any large enough Java footprint, you're going to be spending 15% or so of your time in the garbage collector, which almost always turns the garbage collector into one of your heaviest functions. So you can almost always improve your CPU performance by identifying places where you're allocating too many new objects. And that's for me, coming from a C++ background and generally having like I'm a little bit skeptical of garbage collectors as a concept to some extent. Seeing that's the most common way of optimizing for CPU cycles was certainly a surprise, and not necessarily a pleasant surprise for me, if that makes sense.
Right. So you said 50%, right? 50.
No, 15. No, 15. 15. Yeah.
Yeah. Okay. Well, I mean, yeah. So still, that's a pretty high number. Yeah.
And particularly because you end up having that as a heavy function across many machines, right? Like if you're running, let's say you're running 20 different Java workloads over 2,000 machines, it's very unlikely that any single other Java function is going to be eating 15% of overall cycles, but the garbage collector most likely is.
Yeah, interesting. Now, let's talk about this. Why do you think? And you are actually pointing this out in one of your talks now. Why software vendors now will have more incentives to optimize their code as opposed, for example, to 5 years ago?
Yeah, I mean, you can see that very, very clearly, funnily enough, in stock market data. So if you look at publicly traded SaaS companies, there's a very, very linear relationship between their gross margin and their stock market price. So you can see that if your gross margin is higher, the stock market value is much higher as well. And the way this translates is usually that 10% more gross margin in absolute terms, so your gross margin going from, let's say, 60% to 70%, usually translates into 2.5 times your revenue added to your market capitalization. And that relationship is very, very
Thomas, I think we might lost him due to his issues with the battery. So I guess we'll have to wait for 5 minutes until he will come back. But I mean, sure. Yeah, that's funny. If anyone wants to jump in and share their thoughts while we're waiting, then definitely request the mic. I see a lot of people in the room. That's great. We also have a Discord channel. Sorry about that. I actually should have pasted a lot of links here, like and to everything that we discussed, like Google white papers and so on and so forth. But anyway, we can do it later. In the meantime, let me maybe expand on this thought. Like why software vendors would have more incentives to optimize their software, and my explanation would be that like if we look at the 10 years ago in the PC era, when you were deploying your software essentially on the customer's hardware, and you pretty much don't care about how efficiently the software would run on the customer's hardware, right? It can take 1 minute, it can take 5 minutes. I mean, in the end, you as a software vendor, you are not paying for their electricity bill, right? But now, when you are deploying your software to the cloud, you're essentially like you are paying your so-called cloud bill, and then and this might and if your software is pretty much not efficient, then you will be paying for that inefficiency. So that's one of the reasons why I think in the future more and more people, more and more software vendors will have to to spend human resources and their developers' time and make their code more efficient. If anyone wants to jump in and say a few words, and if anyone has any comments while we're waiting for Thomas, then definitely go ahead. Let me see. So later, I actually wanted to discuss the topic that's like a fleet-wide profiling. It's actually the thing what Thomas is now working on. It's essentially a profiler, a performance profiler, which runs across your well, I mean, across all of the hardware that you have in your ecosystem. Like, if you have a distributed application that runs on multiple hardware instances, then the tool that Thomas and his team is working now allow you to profile all the instances simultaneously and have and have insights during some time span, and then you can do interesting analysis on that data. Yeah, so this is what we will discuss next. Yeah. In the meantime, if anyone wants to share any performance debugging stories from your experience, if if you are working on the cloud applications, then definitely jump in and share your stories. We would love to hear that. Actually, I just went ahead and plugged my phone because I'm also running low on battery. So sorry about that. That happens. I hope Thomas will get back online soon. Oh yeah. Meanwhile, I see Chad shared some link in our Discord channel, so you can also go there. Yeah. So if you want to request the mic and can find the proper way to do it, there is a three dots, and then you can click on request the mic, and then you can and then I will be able to accept your request, and I will give you the mic. Let's see what we also have. Oh, okay. So yeah. For those people, okay, we have some requests. Let's see. Okay. Hey, Thomas, you're back.
Phone died of low battery, and now I've driven home and gotten the charger.
Cool. Meanwhile, Thomas, we have a Harry. Harry, you can talk now.
Hey, Dennis, thanks for organizing this chat. Sure. I had a quick question for you guys. I'm interested to know your thoughts on the cost to serve when companies move to cloud, and companies like Box deciding to move back to their own data center. Netflix is also thinking about something on similar lines. So I wanted to understand what's the benefit versus drawbacks of relying on public clouds like Google or Amazon.
Yeah, I mean, so I think there's pros and cons for both. I think for 95, perhaps 99% of all companies, building their own data center makes no sense anymore, in the sense that you need to have reached a very, very large scale of compute, and you need to have a very clear idea of what your compute will look like in order to build a data center that is going to be like supportive of your business in the way that it needs to be. So meaning we're speaking about the box, we're speaking about Box, and we're speaking about Netflix. Both of these are huge. The cost of compute is a very, very direct part of their margin. And they both don't have issues retaining and hiring engineering staff. And only under these conditions can you even think about building your own data centers again. For everybody else, having somebody else do the operations of the data center is almost certainly going to be the better choice, at least. Yeah, I mean, the thing really is, let's say you're FedEx, right? Your expertise is going to operating the most efficient data center. So it may make sense to just give that to somebody that does have that as core of the DNA, if that makes sense.
Mm-hmm.
While I'm talking about, one thing to keep in mind is that cloud providers still have fairly high margins. So if ever there was a real price war breaking out in cloud, the margins of the cloud providers would erode significantly, hopefully. So that's another thing, right? There is a risk that if you do a huge data center investment, that then a price war amongst cloud providers reduces margins for the cloud providers, which then allows you to reevaluate whether your investment in your own data centers was the right thing to do. That said, you can reduce your like, if you're Netflix, you can likely reduce your computational costs significantly by moving to your own data centers.
Thanks, Thomas. In my experience in some of the companies I've worked, and these were with significantly high workloads already and a big data center footprint. And when we were trying to move some of our workloads to public clouds like AWS, what we saw from our data is the cost to serve was actually much higher with AWS than if we were running it on our own data centers. However, the quality of the infrastructure and the pace of innovation was much higher. So initially the sell within the organization was cost, but it quickly moved to pace of innovation rather than cost.
Yeah. I mean, that makes a lot of sense, right? You don't necessarily want your best engineers to worry about data center, but you want your best engineers to worry about how to please your customers.
Yeah.
Thanks, Harry, for the question. It was a great one. Thomas, now let's talk about the Fleetwide profiling, because I guess this will be a lot of fun. So probably the most folks here already understand why do we need the Fleetwide the Fleetwide profiling, but can you please just reiterate on that point, like why do we need to profile all the hardware?
Happily. So I think there's multiple arguments for this. I'll start with a very high level argument, which is, if you talk to a car manufacturer, the car manufacturer can give you the price for every component that goes into a car. Meaning any screw that goes into the car manufacturer knows what that screw costs to buy, and the car manufacturer can give you a very precise calculable margin that they're generating from the car. And there's an argument that you can't really do any form of margin optimization or any form of efficiency improvement if you can't measure where you're sending all your compute. So software just isn't at the right point. Like few organizations that sell digital goods can provide you information about which of their features are costing them how much money in the end. So one argument for Fleetwide profiling is it's a good idea to just measure where all your CPU cycles are. You can then focus on improving those parts of your infrastructure and just be more efficient there. Other arguments for Fleetwide profiling, you can see this You can see Google built an internal Fleetwide profiler, and then Facebook built an internal Fleetwide profiler. And a number of other companies have begun on the trajectory and may or may not have realized having good Fleetwide profiling. But that only happens after a certain size and a certain engineering sophistication. And in some sense, where Google and Facebook are now, a lot of other businesses will be in a couple of years. I mean, got something like TikTok. TikTok is on a similar, like ByteDance, they're on a similar trajectory to YouTube. Somebody like Spotify will have huge cloud costs and so forth. So summary is, there comes a point in time where you want to have the information about where you're spending all your cycles, and you want to push that information back to the developers. Because in many organizations, you have a disconnect between the developers and the actual cost of compute. So you've got the operations folks, you've got the finance folks, and the development folks. And DevOps was all about getting the developers and the ops folks to integrate more tightly to deliver software more efficiently. Then there's some people that are talking about FinOps, where you have the finance folks and the operations folks that talk about stuff like reserved instance planning in the cloud and other cloud resource planning. But in the end, what you really want is you want to have a dialogue between the devs and the ops and the finance folks, so that you actually know where you're spending all your money, essentially. And my experience has been that once you push information about where all the cycles are being spent back to the developers, a certain subset of the developers, likely the sort of developers that will end up in this call as well, will jump at the opportunity to then fix stuff and make things better, right? Because in the end, we all strive to see impact from our work, and particularly developers' performance will go after that data like a bloodhound of sorts, and then find all the places where cycles are wasted and make everything faster and better. So there's a strong argument that the people in an organization that are actually best positioned to provide more efficient delivery are the developers, but you need to provide them with data so they can make good decisions. And Fleetwide profiling provides that data, if that makes any sense.
Sure. Yeah, that makes sense to me, definitely. But can you please just elaborate on how it will look like? Like, what I mean by that is that how this communication between Fin and Dev will look like. Like, can you give some details? Like, for example, I know that in Google, right? Google integrated this cost function, whatever, in their code review systems, right?
Yeah. So I don't like not necessarily in the code review system, but when you did launch a large computing job, you would get feedback about the cost of that computing job when it was done, not necessarily in terms of dollars, but in terms of your working time. And then the other big piece of the infrastructure that Google has is the Google-wide profiler. And the Google-wide profiler samples across the entire Google fleet and accumulates data about where code is executing in a web interface. And then developers can browse the web interface and inspect their own services, but also inspect the wider fleet to identify how many cores, like cycles or core hours and so forth, are spent in what part of the code base. And yeah, and that's like the usual way to make this work in practice. Let's say you are similarly similarly organized to Google, where you have a monorepo with all the code that's running, just gathering information about which lines of code are eating how many cores, and then having a sort of overlay where you can see in your code which parts of the code are hot, or having a web interface where you can just browse through the performance data for the entire fleet. That's already super useful. So yeah, just having a web interface where you can see across 1,000 machines, 2,000 machines, 5,000 machines, which lines of code are eating how many cycles, and then having the ability to drill down now for this service, which lines of code are eating how much, or aggregate across different services. So for, let's say, STD map, how many STD map inserts do we have across the fleet? So yeah, the summary is you collect that data and then you provide an interface where it can be made inspectable and plausible to developers, and then developers will usually find ways for making things better.
Yeah, that's great. And your mission is to you're on a mission on making this accessible to not just Google and Facebook, but to all the other users that are working in the cloud. Yeah, that's
yeah, correct. So the background there is that both Google and Facebook achieve the whole fleet profiling ability by recompiling everything from scratch with frame pointers. So for those, I mean, we're on a low level-ish call here. So I think the majority of us is familiar with the problems induced by frame pointer omission in binaries and how that affects stack unwinding. And Google and Facebook just compile everything with frame pointers so they can use the frame pointers for unwinding. But normal companies can't just recompile every library from scratch with different compiler options. So what we're doing is we ended up building a bunch of eBPF code that can do stack unwinding of native binaries when frame pointers have been omitted without having symbols available on the machines. And we also have done a lot of work on the individual different language runtimes like Java, Python, Ruby, Perl, Go, yada, yada, yada. And the end effect is that we can deploy a profiling agent on a fleet of machines between like 2 machines or 2,000 machines. And we then attach our eBPF code to the timer software interrupt or to the software clock. And then we sample stack traces across all the different runtimes automatically. And we aggregate all of that in a backend and then provide developers with the ability to sort through that data thereafter. And yeah, that's what we've been spending the last 2 years on. And if anybody wants to try, hit me up via direct message on Twitter, and we're onboarding people into our beta program and expect to launch hopefully in late August.
In August. Whoa, wow, cool. So that's in this month. That's great. So again, let's do a DFS one more time. So you are talking about symbols, right? So I'm actually curious. So I took a look at the user interface of your tool called Profiler, right? So one question that I have is how do you actually obtain the symbols? So it's not frame pointer. So you must be using debug information, right?
Yeah, so we don't use debug information on the machines where we're doing profiling. We actually use some of our security low-level expertise to find a way to do stack unwinding with no debug symbols present on the machine. We do use debug symbols in our backend to symbolize those traces and make them readable. So on the machines themselves, we just sample the stack traces. So we just get file ID and offset pairs. This stack trace here goes through this file at that offset, that file at this offset, and so forth. And we accumulate all that data in the backend. And then in our backend, we also have indexed all the debug symbols from upstream Debian, Ubuntu, and Red Hat repositories. So if you're using any upstream packages, we can automatically symbolize those for you in our backend. And for any libraries that you've built custom or that aren't in the upstream, you can upload the symbols into our backend, and then we can do the symbolization for you. And the advantage of this is that you don't need to have debug symbols on the production machines where we're doing the sampling. Because our experience prior to building Profiler was there was always a pain to hunt down all the places where debug symbols are from. And then also it was a pain on to have these debug symbols on the production machines.
Right. I'm still trying to wrap my head around how you would do that. But okay, so I assume, well, okay, so you said you're utilizing your low level expertise and hack in some way and unwind the stack without actually unwinding and get the stack traces. I assume your life would be much easier if you would have something like LBR, like the last branch record, available on every platform. That would make your life significantly easier. You can just collect the stacks with LBR, and then again and then do your magic in the backend. But okay, so but how you and then you somehow need to upload or how do you, I mean but okay, so assume your binary in the cloud runs without symbols, right? But then how
Yep.
do you, on the backend side, how do you get those symbols? You're
Yep. So
upload them in a dwarf dwarf section, so you strip the debug
yeah,
section and then upload them, or
yeah,
how
yeah,
do you solve
correct.
this?
Yeah, so the way we solve this currently is you can upload the symbol, like essentially a dwarf symbol section to us, and then we'll use that for symbolization. And that's the way you utilize stuff in our backend. In the future, we're also planning to do approximate symbolization for situations where you can't, like we sometimes, for example, see people deploying, let's say, a Postgres container, and we can't find the original symbols for that Postgres container. Now, given that in my previous career I worked on tools to do comparisons between binaries that were used for porting symbols from one binary into another, one thing we have on our roadmap is to start symbolizing traces even if the symbols we have are not for the precise same binary and just for a closely related. And the reason why this is important is a lot of the Python ecosystem, when you do a pip install of a given package, quite a few libraries will ship source code to the machine and it'll be compiled on that machine, which means there will never be an upstream debug package of sorts, and you need to be able to symbolize those traces through the C++ library nonetheless, even if you only have a very similar but not identical binary. We don't do that yet. So at the moment, the way to symbolize stuff is still upload the symbols to our backend, and we do the symbolization for you.
I see. Yeah. Okay. Let now go a little bit back and actually, so Thomas, let's so can you explain why it's not sufficient to profile on your local system? Why do you need to profile on production systems?
Yeah, so the reason for this is that software has changed in the sense that the majority of software these days is a large distributed system running on many machines, on large volumes of data. The time where you would run a piece of software on one machine is just largely gone. Like most infrastructures these days, you run on many machines, and also production traffic is always quite different to your local machine. So you just won't get accurate data if you're just running on synthetic traffic on your own machine. Lastly, there's surprises in production systems that you won't be able to reproduce easily on your laptop. One of the huge advantages of having continuous profiling everywhere is, let's say on a Sunday morning when everybody is home, out of a sudden you see a few machines go into 100% CPU utilization and stay there for a couple seconds and just have a big CPU spike there. Being able to go back in time and ask, hey, what stack traces did we sample on Sunday morning, 4 a.m. when these CPUs went crazy? That's super valuable for debugging production systems as well. And lastly, sometimes you will hit pathological cases in production that you will never hit in your own testing. And by having profiling data for your production systems, it gets much easier to isolate which parts of the code are pathological. I mean, the joke is that the way to get performance problems in production is always an accidentally quadratic algorithm somewhere, which is fast enough to pass through tests because your test samples don't quite hit the steep part of the quadratic curve yet. But then at some point they blow up in production. And then having the ability to compare workloads in production and see, hey, it's these lines of code that are eating way more CPU at 4 a.m. here when the spike happened than at 3 a.m. when the spike didn't happen, allows you to drill down on the problem really quickly and fix stuff. So I think this was a very long answer for nowadays in most infrastructures, production does not equal what you're developing on your workstation anymore.
Right. Yeah, that's true. By the way, do you have any kind of cool, interesting performance debugging stories that you want to share? Maybe.
Yeah, I mean, there's interesting ones all over the place. I mentioned the misconfigured timer source in AWS instances earlier, which is still one of my favorite ones. But other things we've seen is we once we were doing performance optimization for a company that was ingesting a lot of data from the internet and then essentially running that through a large number of regular expressions and then writing the results into a database to surface the results to users. And profiling that infrastructure, it first revealed that for some reason an upstream regular expression package had disabled the just-in-time compilation for regexps. So you could just improve the performance drastically by enabling jitting. And then the next thing we found was that a lot of time was spent in the library bindings between Python and that regex library, looking for non-ASCII characters in the strings to run regex over. And for some reason, the compiler had failed to vectorize that loop, so we had to manually vectorize it, and then that generated huge performance improvements. So what I've always found is you get these strange murder mysteries where something that you really didn't expect taking so many cycles ends up taking so many cycles. And there's a surprising number of low-hanging fruit, like where what you need to do is actually relatively little and the impact is quite large. Be it vectorizing the right loop or changing the right configuration in an upstream library. That said, there are a bunch of performance analysis problems that I found to be tremendously hard, particularly when it comes to analyzing why a particular compiler flag degrades or improves performance. Because what I found is that in modern compilers, especially when you have PGO and LTO enabled, you have a lot of cascading effects where like a change somewhere can cause other changes in the compilation. And then sometimes you get a change like adding LTO or PGO, which degrades performance. And I found it's really tricky to really nail down why isn't this giving us extra performance. And that's also frustrating because to me as a tool builder, it feels like there should be better tooling to answer questions like, why is this compiler setting degrading performance and not improving performance? Am I making sense?
Yeah, that makes sense to me, definitely. I mean, I probably can imagine how PGO can or profile guided optimizations can degrade performance, but I'm having a hard time trying to figure out how LTO can degrade performance. Can you?
So
do you have any examples?
So I think the way LTO can degrade performance is mostly by making workloads more front-end bound. Because LTO can do much more aggressive inlining and by that increase code size much more.
I see.
And particularly when coupled with bad profiles, like the way to degrade performance using LTO is in a combination of LTO bad PGO profiles, because then the compiler will make a lot of decisions where code size is increased for the wrong paths to inline.
Right. Yeah, it makes sense to me. But still, I mean, your tool is not in control of how users compile the binary, right? Is that correct?
Yeah, so we're not in control of how the users compile the binary, but what we are working on is the ability to download data for feeding it into the compiler for PGO from your production workload. So I think this October, we should have a REST API where you can say, hey, my PGO data for this executable, I would like to rebuild with profiling data from production. Because in my view, PGO with profiling data, I mean, Facebook and Google use it all the time and everywhere, but it's almost criminally underused everywhere else because it's so difficult to get good profiling data from production for everybody else. So
Right.
we definitely want to make PGO for everybody from production data easy.
Yeah, that's I think will be a great feature to have, because that's essentially a free speed up. Well, I mean, in most of the case, and if you will not speed up, then yes.
Yeah.
Yeah, that's great. But let's now go a little bit back again and talk about what is the use case, and how to get started using your profiler.
Oh, it's relatively easy. If you have a lot of CPU cycles being spent on the cloud and you want to know which lines of code are eating them, hit me up on direct message and we'll see whether we can get you started. And then the actual workflow is pretty easy. You sign up, you get a link from which you can deploy a Docker container on your machines. And the Docker container contains the profiling agent, and then half an hour later, you've got profiling data that you can start inspecting. And you can then go and see whether you've got any low-hanging fruit. And more often than not, there will be surprises in that data that nobody anticipated. I think the rule of thumb for almost everybody is the entire industry is spending way much more CPU time on serialization and deserialization than we should. We ran a very big Spark distributed machine learning workload that CERN had published recently, and we were quite astonished that of the overall workload, like 20% of the time was spent in Python deserializing stuff from Pickle, and in Java serializing to Python's Pickle. So it was a big PySpark workload. So you have a large data set that is eaten by a distributed cluster of machines, and the Java code then serializes the code into a form that Python can eat, calls Python deserializes the data, and then starts processing it. So you end up with a large distributed workload where you're spending 30% of your entire CPU time just serializing and deserializing data. And I'm always astonished where cycles are going.
Right. So let's now talk. So we mentioned already call stacks, but for those people who maybe are concept, so can you please explain what is call stacks and why you need them and how they will help people to optimize?
Cool. Yeah, so I mean the rule of thumb is if you have a CPU and you get a timer interrupt, you can tell at what address that CPU is executing. And the trouble is that the address where you're executing doesn't tell you yet how did the CPU get there. It's easy to find out where's the CPU running now, and then the call stack to understand how did it get there. So for example, let's say you get the time interrupt, and it turns out you're currently in the kernel moving VMAs, which is a certain data structure in the kernel, around. And then the call stacks can help you answer why are we doing this currently. So the call stack may tell you, okay, we're now unwinding the call stack through the kernel, and we end up in some, let's say, mmap syscall. So the VMAs are being moved because somebody's calling mmap. And then you unwind the user space call stack, and you may end up in the standard libc where somebody's doing a realloc on a piece of memory. So you unwind further, and then the realloc is actually called out of a, let's say, a C library, and you unwind further, and you end up in Python code, and then the Python stack contains some Python functions that eventually do something like a piece of graphics. So what is happening is if you have a stack that can unwind all the way from the kernel through user space libraries into your high-level language, the stack provides some information about why. Meaning the place where your CPU is executing tells you what, and the stack can tell you some information about why are you doing this at the moment. And when it comes to profiling, this why is actually critically important. Because you will need to understand why you're spending your time on a particular problem anyhow. And then these stack traces can be aggregated and visualized in multiple different ways. Brendan Gregg popularized flames, which are one way of visualizing stack traces in aggregate. And then the Go tooling generates call graphs out of this. And we do the same in our web interface. So it helps you understand how many CPUs are inside a given function, and the children of that function and their children and so forth. Yeah, I hope that was a useful explanation. I will have to ask somebody whether it was later.
Yeah, that's a good explanation. One thing I'm actually curious is that do you have a problem of matching call stacks from machines collected from different machines? Because, like, I mean, so for example, it is the same. It is the same, let's say, tree, or it is well, I mean, the same call stack, but it differs in a way just because of the differences like on two different systems.
So,
do you have like the problem matching those stacks?
We usually do not have a huge problem matching if we can get symbols. So let's say the biggest issue is, for example, if you're doing profiling for anything that is just in time compiled, your addresses will be different on every CPU run or on every run of the program, and you have to essentially symbolize those addresses before you can do any grouping. And for just-in-time compiled code, we do the symbolization when we collect that data. For executables, you need to account for address space randomization. But once you account for address space randomization and the executables are the same, then the call stacks will be matched easily. Things get a bit trickier when the executables aren't precisely the same, in which case we need symbols to match things properly. But in general, that works nicely. What's a bigger problem, though, in a microservices architecture is I would love to have a combination of profiling and distributed tracing, because in some sense, a call stack only gives you information about one machine. But if you want to answer the question why in a microservices architecture, you kind of don't only want the call stack of the machine or of that piece of program right now. You would kind of like to know, hey, the thing I'm doing here, I'm doing because another machine sent me an RPC of sorts. Which machine sent this? Or like just having more context about the cross-machine communication. But that's very difficult to do, and I don't quite know how we'll get there yet. So that's more me dreaming into the future. What sort of tools would I like to have in 5 years?
Cool. Well, I mean, collecting stacks is well, I mean, quite add quite some overhead, right? So how do you process that in a real time? Yeah. And then like, do you have like latency, and how big is this latency?
Yeah. So we try to keep the performance impact of collecting stacks minimal by a variety of different things. The first one is we do all the stack unwinding and like everything involved with that in kernel space from eBPF, which reduces the number of context switches that you have to do. So you essentially get the time interrupt, you do the stack unwind, you then hash the stack that you've obtained, and you just increment a counter for the hash of that stack. So we keep the amount of actual data collection that we need to do minimal, and we keep the number of context switches we have to do minimal. The other thing that we do is we keep the actual sampling rate reasonably low, because if you have, like, in the end, in order to get a statistically representative sample, it doesn't really matter whether you're in 100 times or 1,000 times per second on one machine, or 100 times per second on 10 machines, right? So what you can do is you can reduce the sampling rate. If the fleet of machines you're profiling is larger, you get an approximately decent representation of the workload. Yeah, and then so we've got knob number one, or point number one, do as little work as possible. Point number two, reduce the sampling rate so the performance impact is agreeable to the user. And then number three is if the reduced sampling rate still isn't enough, you can have a changing percentage of your fleet sample at any point in time. So the ideal scenario, of course, if you want to have all the data, is sample everywhere all the time. But what you can do is you can say, okay, we're only going to sample on 5% of the fleet, and then every minute we change which 5% of the fleet that is.
Right, that makes sense. Do you have any idea of what can be the overhead, like the number? Do you have any estimates?
So we're targeting at any time less than 1% of the total CPU.
Less than 1%.
And by and large, we are significantly below that for most workloads. The one type of workloads where we get into trouble is something that is extremely fork heavy. So every time you spawn a new process, we need to do some housekeeping in the kernel to make sure we can unwind the stacks properly. And that housekeeping therefore is linear in the number of forks that you do, which then means that for the majority for essentially every real production workload, we're comfortably below the 1%. But for the usual nerd benchmark of let's recompile the Linux kernel, we're actually above 1%, like 2, 3, sometimes 4%, because the Linux kernel compile is just you're spawning GCC in a highly parallel manner on many cores, and that's more or less a pessimal workload for us. So long story short, we're comfortably below 1% for normal production workloads. If you spawn lots and lots of processes all the time, we're above it.
Great. That's actually great. Yeah. What other metrics do you collect?
So at the moment, we're only gathering stack traces and CPU and I/O utilization. What we want to do in the future is we want to do I/O profiling in the same manner. So question, which stack traces are eating our I/O ops? And something we want to do in the future as well, but that's going to be a fair bit of load, is better memory profiling for native code. So in essence, asking the question, hey, can we sample stack traces for allocations? Lastly, one of the things that we also want to do is we think there's tremendous value in combining profiling data with other metrics. In the end, you want to get to something like an eye to present to management, like the number of CPU cycles spent for a song played, or the number of CPU cycles spent for like a meal delivered if you're Uber Eats or whatever. And in the end, you want to be able to tell management, hey, the cost of playing a song has gone up because this part of the code here has gotten less efficient. And in order to do that, you need to combine profiling data with business metrics. And that's something that we're really, really interested in doing. And we'll try to in the future.
That sounds great. One follow-up question I have is, do you think that the cloud service providers would be interested in integrating your tool and make it native? So, right. So, and but by the way, so how do you actually now? So the user now has to run manually the tool, right, via some scripts, I would say, or some commands, right? So do you think that the cloud service providers would be interested in integrating that tool into their ecosystem and make them available for the users?
So I will, right? I mean, to some extent, we're building this tooling because we think this is a useful thing to have for everybody, including the cloud service providers. So clearly, I would hope that cloud providers want to have this as a standard feature in their platform. And clearly, we would want that to be a standard feature in their platform as well, because we want people to use our stuff. But beyond that, I don't think I can say much about, like, I'm not a cloud provider, so I can't tell what their priorities are at the moment.
Sure. Yeah, but at least to me, this sounds interesting, that to have as a native tool, right, of the cloud ecosystem.
Yeah, definitely it would be, and it would be useful as a native tool for their clients. It would be future. It would be, like, in general, it would be a fantastically useful technology.
Yeah, I agree. And given that all the major players now somehow have some sort of telemetry systems, that's for now it's a privilege of the big companies, but well, maybe we'll have that available for let's say average users. So yeah, that's great, and thanks for doing that. I think that's actually all the questions that I have for performance in the cloud and Fleetwide providing if anyone in the room wants to ask questions, actually, sorry for missing all the questions from the chat. There are a few questions, I guess. But by the way, if anyone here in the room wants to ask the question live, you can do it. That's now a good time to ask questions. If not, we will wrap up slowly.
Yeah, and regarding the chat, I'll join the chat. Like, I have to bring my kids to bed, but once the kids are asleep, I'll join the chat questions that came there.
Yeah, sure. Thanks, Thomas. No worries. We have a question from Chad. What will win as a control plane? Is one more cost efficient at scale, Kubernetes or AWS Zelkova SMT solver?
I don't know. I mean, I don't know the actual cost of the control planes. So it's a good question, but I don't have the answer.
Okay, so we have a embedded cat. Embedded cat, you're now able to ask question.
Yeah, hello. Thank you very much. I'm actually coming as my name from the embedded world. Is that something that you think that you actually? I'm coming from the packet processing, when we are doing a lot of and very to the nanoseconds profiling in switching and routing. Is that something that you think that will help also the embedded world, or do?
So we are planning on supporting ARM64 later this year. I have to admit that I don't have enough experience in the embedded super low latency switching world to really judge whether what we do is a good fit. We'd be happy to try, and we'd be happy to chat with people from that world. But before I make promises, I want to actually talk to somebody. I don't think I have the expertise to confidently say yes or no to that, if that makes sense.
Yeah, that will be very interesting to test because our tools are relatively limited. So we have to guess a lot of time. And the interesting thing about embedded that we have a lot of devices in the field that are actually getting real profiling data. So that can maybe be a good for that. So
what operating system kernels are you running normally? Because we need a Linux kernel of 4.15 or higher because we're using eBPF.
Most systems that I know about running above that.
Okay.
So it's not an issue.
Cool. Well, yeah. Ping me. I'd be interested to give it a spin.
Okay. Thank you. Thank you.
Okay, well, Thomas, let me ask you, a couple of, personal questions, if you don't mind.
Sure.
So, do you have any suggestions for books, podcasts, whatever, blogs you are reading, and just share in general how do you educate yourself?
So I think, weird as it sounds, having a carefully curated performance-related Twitter feed has been very, very useful. Because the one thing I find a little bit sad about the performance community is we don't really have the one place where we congregate yet, right? It's quite scattered. There's a few people on Twitter. There's a good idea is usually figuring out who's retweeting Agnes Foch research into CPU latencies and stuff. So yeah, it's EasyPerf is a good resource. Then the Twitter feeds of people like Travis Downs and Lemire and Geoff Langdale, and the EasyPerf Discord is something that I should probably hang out on more. What I've always wished there was, wish there was like a big perf, like infrastructure perf Slack, where people hang out and just talk about I come from the IRC, meaning the original the copy protection removal scene, and then the security scene. And back in the days, there were IRCs or IRC channels for particular topics. I haven't quite found the Slack or the IRC channel where everybody discusses and shares performance things. There's different channels here and there, but there's not the one key that one can easily join. And I think doing community building around profiling, performance optimization, and all of these things would be a tremendously useful thing to do. And I'm actually happy that EasyPerf exists, because I think it's got the potential to do more of that and become important there.
Oh, thanks. Thanks for the kind words. So yeah, I mean, I actually agree with you that that this knowledge is somehow scattered around, not approached in a systematic way, if you will. Yeah, I mean, there are a lot of performance ninjas, that just know their stuff, not necessarily sharing their knowledge with others. And yeah, so when we end up we end up having this this kind of knowledge, not I would say not very much accessible to other people. So yeah, but at the same time, this is a really hard topic, and at the same time, this topic might be very much more important in the future than it was in the last decades. Even.
Yeah. And I mean, if you look at the trajectory of security information, the amount of information that was available in the late 90s was very, very little. And nowadays, there's just a wealth of info. So my expectation is that performance, similarly, over the next 10 years, all these scattered with expertise will need to form into bigger entities of sorts that gather expertise.
Right. Yeah. I agree, definitely. Let me actually ask you this question that I'm personally interested in. So you have so Thomas, you actually have a very strong personal brand, right? So you have more than 30,000 subscribers on Twitter. Many people value your opinion. So tell me, please, how did you get there, and does it help you in any way?
So that's a good question. The issue with a lot of these questions, like how did you get there, is you ask somebody that fell out of an airplane and miraculously survived, how did you do it? Right? And I'm not sure I know. When it comes to my Twitter feed, of course, having been very prolific in the security community for a long time helps. Time helps. I mean, I've been active on Twitter since 2008. And then trying to post interesting and meaningful things for 10 years will eventually get you more followers, I guess. But yeah, it's I guess the thing that worked best for me was try to always be learning. And whenever I had understood something at sufficient depth, try to explain it simply. And that usually got, like, if you look at the for example, my talk about the complexity and the end of Moore's law, that was actually a fairly complicated talk when you think about the subject that it talks about, but it's reasonably accessible. So I think one of the important ways of building a good audience is making difficult things or complicated things more accessible, because that'll automatically attract people that are in, if that makes sense.
Definitely. Yeah, definitely makes sense to me. Yeah, and thanks for all the work you are doing. Okay, Thomas, that's it was great having you today. Thanks for coming, and thanks for finding time. I know, I mean, as a parent myself, I know how hard it is sometimes to find a few hours of a free time. So yeah, thanks a lot. And then so how people can find you online, and specifically how people can find the work you are doing with Profiler.
Yeah, so online, the easiest way to find me is Halvar Flake on Twitter. And then we do have a website at optimize.cloud, but it's outdated and has no information about profilers. So at this point in time, the best way is, sadly, ping me on direct message on Twitter or send me an email to Thomas Dullien at optimize.cloud. And then I'll get back to you quickly. And as I said, we hope to be launching in late August in some sense, and then we'll also have a better website with more information by then. Sorry for that. And again, thanks for having me here. It's been a blast.
Sure. Thank you, Thomas. Thanks a lot. To everyone else, see you in 2 weeks.
Awesome. Thank you. Bye-bye.
Have a good rest of the day. Bye-bye.
Bye-bye.